Welcome to Casting Academy. Today, our important topic is engineering materials. Particularly, now we are in the portion of structure of solids. Structure of solids. Most of the engineering materials are solids. The physical structure of solid materials depend mainly upon arrangement of atoms, ions, or molecules which make up the solids. As you know, atoms, ions, or molecules make up the solids. If the atoms of a solid are arranged in a repetitive three-dimensional pattern, then the solid is known as crystalline solid. Crystalline solid means the atoms are arranged in a repetitive manner. Certain solids do not have such repetitive three-dimensional pattern. Such kind is non-crystalline amorphous solid. Non-crystalline amorphous solid. So crystalline solid are amorphous solids. Metals are and some ceramics have crystalline structure, and other ceramics and polymers have glassified as non-crystalline structure. Now you are seeing the crystal structure. So, crystal structure, the regular repetitive arrangement of atoms are described by three-dimensional network called space lattice. Here, space lattice means regular arrangement of atoms are described by three-dimensional network, that is called space lattice. Space lattice is a three-dimensional pattern of points called lattice points in corners. Each point in the space lattice have identical surroundings. The smallest component of the space lattice is a unit cell that retains the overall characteristics of the lattice. The size and shape of unit cell is described by three edge lengths A, B, C, and the interaxial angles alpha, beta, gamma, known as lattice parameters. You see the lattice structure, crystal structure. So these corner points are lattice point, the edge length is A, B, C, and angle between those is alpha, beta, and gamma. Now Bravi's lattice. According to the lattice parameter, there are 7 crystal systems having 14 types of space lattice called Bravi's lattices. First you see the structure. First one is cubic structure. Such a cube, all the sides are equal length A, A equal to B equal to C, and the angle between the ABC equal to 90 degree. Second one is the same cubic structure with the face center, body centered atom in central portion of the body. So this one is face centered structure. Second structure is tetragonal. In tetragonal, the edge length A equal to B, that is not equal to C, and alpha beta equal to 90 degree. This is the FCC tetragonal structure. Orthorhombic, here you are seeing orthorhombic, that is A equal to B equal to C, not equal to C. All are not equal to 1, and alpha beta gamma equal to 90 degree. The same structure with the body centered and face centered structure. And hexagonal. Here the hexagonal structure, A equal to B, that is not equal to C, and alpha beta equal to 90 degree and gamma equal to 120 degree. Trigonal, monoclinic. In monoclinic, A equal to B equal to not equal to C, and alpha gamma equal to 90 degree, beta equal to 120 degree. Triclinic. Now, the types of unit cell: P primitive, I body centered, F face centered, C side centered, 7 crystal classes, 14 Bravis lattices. Now, the metallic crystal structures, most materials either body centered, face centered, hexagonal close packed structure. So now we find the crystal system such a type body centered BCC, face-centered FCC, hexagonal close-faxed HCP. Here the body is BCC structure, body-centered cubic structure. You see, body-centered cubic structure. So these are all the corner atoms, 4 corner atoms. With this center one is the body-centered structure. Here you see the body-centered structure. All the 4 corner atoms are quarter corner atoms. This is the arrangement of BCC structure. So in BCC, the unit cell has one atom at each corner. As you see, one atom at each corner and one atom at the center of the cube. That is the main idea. In BCC, corner atoms shared by 8 unit cells, nearby 8 unit cells, and interior atom only one cell. So FCC structure, the number of atoms per unit cell is 2. That is 2. In BCC, the atoms touch along the body diagonal, which is root 3a in length. As you know, the diagonal length is cube equal to root 3. That we have the root 3a equal to, that is its diagonal length. There are 2 atomic radii from the corner atoms and 1 atomic radius from each corner atoms. The diagonal is 4r, that is equal to root 3a, a equal to 4 into root 3. Here the term is coordination number is the number of atoms touching particular atom or the number of near neighbors. In BCC, each corner atom is surrounded by 8 other body-centered atoms. Hence, the coordination number is 8. The atomic packing factor is the ratio of the volume occupied by the atoms in an unit cell to the total volume of the unit cell. Here the atomic packing factor, number of atoms per unit cell into volume of an atom divided by volume of unit cell. Body-centered cubic structure has a packing factor of 0.68, which means 68% of the atom filled with the matter. That is the idea. BCC structure has 68% body-centered percentage of packing factor. Next, FCC structure. Here you see FCC structure. All the faces, all the faces we have one complete atoms as well as corner atoms. That is called face-centered cubic structure. See the face-centered cubic structure. So all the face we have the one atom, particularly half atoms. In FCC, there is one atom at each corner of the cube and one atom at the center of each face. In FCC, overall atoms per unit cell is 4. 8 into 1 by 8 plus 6 into half. That is the idea. In FCC, atom touch along the facial diagonal of the cube, which is root 2a. There are 2 atomic radii from the face-centered atom, 1 atomic radius from each corner. So we have 4 into r by root 2. The atomic packing factor for FCC is 0.74. So better arrangement than the body-centered. In FCC structure, we have 74% of the packing factor. Now you see the HCP structure, hexagonal close packed structure. You see the all corner atoms as well as the center portion we have 3 atoms. In HCP, there are 2 lattice basal planes, top bottom 2 lattice planes, the regular hexagons with the corner atoms, each of the hexagon and atom at the center of the basal planes. Another plane that provides 3 additional atoms to the unit cell. In HCP, corner atoms shared by 6 cells. So finally we got 6. In HCP atom touch along the base side of there are 2 atomic radius from the corner atoms. That's why we have A equal to 2R. So the ratio is 1.633. In HCP center of the basal plane is 6 surrounding corner atoms. There are from the plane. So atomic factor 0.74. So HCP structure atomic packing factor is 0.74. So that's a comparison of metallic crystals. Characteristics. As you know, atoms per unit cell, body centered cubic to face centered for HCP 6. So we have HCP structure is more dense than the other two. A versus R. A equal to 4R by root 3 and A equal to 4R by root 2. A equal to 2R. Coordination number 8, 12, 12. So HCP has coordination number is 12. Packing factor highest is 0.74, which is in body centered, face centered and HCP. Typical materials. So here body centered cubic is tin, tungsten, molybdenum, ferrous, niobium, Kevlar, sodium, vanadium, chromium, zircon, like this. And FCC, ferrous, cubic, aluminium, AuAg, FB, nickel, etc. The HCP in tin, Mg, Zeton, Be, Co, cadmium. Finally, cadmium. So these are all the comparison of metallic crystal structures. Next, direction and plane in unit cell. Directions and plane in unit cell. There is frequent need of identify the specific direction in crystal lattice, especially required for materials and alloys that have properties which have with the crystallographic directions. So in a material, the property is mainly depends upon the direction of the crystalline structure. Certain plane of atoms in crystal lattice are also significant. For example, metal deform along the plane of atoms that most tightly packed together. So it is necessary to use some convenient to specify the direction of planes. Because of the direction is very important in the case of properties of material, we want to show the directions. We want to draw or show. So notation was made popular by the English crystallographer Miller, and hence the indices are called Miller indices. Here you see the Miller indices. Body centered in a BCC structure, we have all 4 corner atoms. So we have 3-dimensional axis, 3 x, y, z. So such kind is we have unit length of, that's why x equal to 0, y equal to 0, and here the another one is 1, 1, 2. So how we will find the Miller indices? First you know the procedure. First you know, yeah, the vector of convenient length is positioned such that passes through the coordinate system. You see the coordinate origin point. The length of the vector projections on each of 3 axes is determined. These are measured in terms of unit cell dimensions. These 3 numbers are multiplied or divided by a common factor to reduce them to a integer values. The 3-dimensional indices are enclosed in a square bracket UVW. Certain group of directions are said to be crystallographic equivalent when the atomic spacing along each direction is the same. So here the number 100010001. So what I am trying is Miller indices have the position of um, lattice in the XYZ axis. That is the idea behind the Miller indices. Here the Miller indices planes, as you know. So this one is 100 and 110, and this is 11111. So like these other remaining structures. So this is crystallographic planes, that is Miller planes. The procedure for finding Miller indices for planes is given below. Determine the intercept of the plane in terms of the crystallographic XYZ axis. From the reciprocal of the intercepts, a plane parallel to the axis may be considered as a infinite intercept and therefore zero index. These numbers are changed to that set of smallest integers by multiplication or division using a common factor. Finally, the integers are enclosed with the parenthesis HKL. So here we are 100, 110, and 111 is the Miller indices plane coordinate axis. Crystallization of metals. So crystallization or solidification is the process of transformation of a metal from liquid state to solid state, in which crystalline lattice is formed and finally crystal appear. So crystallization means solidification of metals. So nuclei formation. When the liquid is cooled, some atoms group exactly corresponding space lattice. These groups are not permitted by the continually breakup. When the temperature is further decreased, the life of the group increases and reaches the critical size. The cluster of atoms bonded together, which is larger than the critical size, is called the nucleus. The nucleus is simple unit appropriate crystal lattice and form the crystal growth. So this is the crystalline of formation of metal. So first one, small nuclei act as center for crystal boundaries. Dendrites continues to grow, grain boundary, and small dendrites, space between the dendrites. So liquid to solid. Here first you see the figure. First, crystal growth. In liquid state, small nuclei act as centers for crystal growth. Next stage, dendrites continue to grow, grain boundary, small dendrites. As the dendrites grow, the space between them fill. Here you see the structure. So crystal growth. When the temperature of the liquid is dropped further, the number of nuclei are formed simultaneously. They are centers of crystallization. The crystal develops by the addition of atoms according to the lattice point it follows. Crystal growth continues in 3 dimensions as the atoms attach themselves. Certain preferred orientations usually along the axis of the crystal. The dendrite arms continues to grow and thicken. The unit cell is mad with the neighboring growth. Further growth of the each dendrite is obstructed by of the neighbors. The trapped atoms in between the arms of the dendrites solidify the disordered manner and form the crystal boundaries. The crystals in the solidified metals are called grains, and the surfaces of between them are grain boundaries. So this is crystal growth. And finally, the interesting topic is crystal defects. In nature, any material have some defects. The real crystal or in cast or weld substrate contain larger number of various defects or imperfections. The crystal defects is meant as lattice irregularly having one more or one of its more dimensions on of its atomic diameter. The crystal defects is affect on extremely small fractions of the atoms, but they are crucial in determining the mechanical properties such as strength, hardness, and ductility of the structure. Crystal defects. So for number one is point defect, line defect, and planar defect. So in point defect, we have vacancy, interstitial, substitutional, Frankel, Schottky defect. These are all the point defect. So line defect, edge, screw, edge dislocation, screw dislocation. These are the line defects. Finally, grain boundary and twin boundaries are in the case of planar defects. So now we will go one by one. Point defects. Point defect means so regularly arranged atoms are replaced by some points are missing. That is the idea behind the point defects. Here you see the vacancy formed. So interstitial also happen. So regularly arrangement is missed on the vacancy with the interstitial. Substitutional impurity also. So this is called point defect. In this we have Frankel and Schottky defect. Point defect means in regular arrangement we have missed one vacancy, missed as a vacancy, and in between one is placed, one atom is placed, and also substitutional in between the gap also. So both we segregate Frankel and Schottky defect. How it will happen now we are saying. The defects are localized distribution of three crystal lattice involving one or more atoms. These imperfections are introduced by the movement of atoms when they gain energy by heating during the process of materials. The introduction of impurities are intentionally through allying. Vacancies. Vacancy is produced when an atom is missing from a normal site. Vacancies are into the crystalline during solidification, high temperature, or a consequence of radiation damage. Interstitial atom. If a foreign atom of entering a crystalline solid occupies the interstitial space between the parent matrix solvent, and such an atom is referred as to a interstitial of atom. Substitutional atom. If a foreign atom knocks out parent atoms and knocks out the parent atom, such atom is called as the substitutional atom. Frankel defect. In an ionic solid, sometimes a long ion jump from the normal lattice point to an interstitial lattice, leaving behind the vacancy. This results in a vacancy of interstitial pair called Frankel defect. So Frankel defect means in an ionic solid, sometimes an ion jump or a normal lattice point to an interstitial site, leaving behind a vacancy. This results in vacancy in interstitial pair called Frankel defect. Schottky defect. Schottky defect is a pair of vacancies in an ionically bonded material. The both an anion and cation found missing from the lattice. So this is the case of Frankel and Schottky defect. Next, line defects. First you see the figure. So regular lines are disturbed. Regular lines are disturbed. So line defects, as you see. So Burger vectors. So this is the case. You see the arrangements. So line defects in crystalline solids are defects that cause lattice distortion around a line. So distortion around a line. part of the line of the atoms will be missing from its regular site, and its missing row is called dislocation. Missing row is called dislocation. Edge dislocation. An edge dislocation is created in the crystal due to the insertion of an extra half plane of atoms. The atoms above the edge of the extra plane are squeezed together and they are in the state of compression. Just below the extra plane, atoms pulled apart and area in state of tension. The edge dislocation said to be positive, denoted with the insertion of extra plane from the top of the crystal. This indicates the negative dislocation, which the uh, of an extra plane is formed bottom of the crystal. The dislocation line characterized by a vector called Burger vector. Burger's vectors is perpendicular to the edge dislocation line. Next, screw dislocation. First you see the figure first, screw dislocation. You see the area, screw dislocation. Screw dislocation is imaginated by cutting a part way through a perfect crystal, then skewing it by one atom spacing. The name screw dislocation is given because it transforms successive atoms points planes into the surface of a helix dislocation line. In screw dislocation, region of shear strain is created along the screw dislocation. The screw dislocation is represented by or according to its helical screw path direction. The Burger vectors is parallel to the screw dislocation. Burger vector is parallel to the screw dislocation. And planar defects. So you see the planar defects. In planar defects are two-dimensional in the mathematical sense and refer to regions of distortion that lie about a surface having thickness of few atomic diameters. Grain boundaries. When solidification of the metal is completed, the grains formed in different orientation join together and form grain boundaries with the atoms irregularly arranged. This is a region of transition where the atomic packing is imperfect. Small angle boundaries. A small angle boundary is an array of dislocation that produces a small misorientation between the adjoining lattices. Twin boundaries. A twin boundary is a plane across which there is a mirror image misorientation of the lattice structure. These are formed during the deformation of metals or annealing. Finally, here what I am trying to explain is various point defects. As you know, every metal in naturally we have metals having some defects. That defects are explained in